Hello, hello, hello. This is Nicholas on this lovely Wednesday afternoon, wanting to really talk to you today about what exactly is a matrix. See, a lot of times in like a high school, maybe a pre-calculus class or something, they might be introduced, and you really have no sense of what they are beyond being just this random array of numbers, right? You know, like you might see something like the matrix 1, 2, 3, 4, and this doesn't really mean anything to you beyond just it's a 2 by 2 array of numbers. Now, if you're a computer scientist, maybe that's good enough for you. If you're a physicist, you're going to get a different answer than what I'm about to give. But really, I think that the answer from a mathematician is the best answer, and so I'm going to give that one. Now, before we can talk about what exactly is a matrix, we need to talk about linear transformations. And really, the answer that I'm going to give is that a matrix is a linear transformation. So linear transformation is a subset of multivariable functions. So, and they're multivariable functions that have the two properties. Essentially linearity, right? So the transformation on the vector x plus the vector y is the transformation on the vector x plus the transformation on the vector y. And then the second property being that the transformation of any scalar multiple of a vector is going to be a scalar multiple of the transformation on the original vector. And these two combined together essentially give that t of c sub 1x plus c sub 2y is equal to c sub 1 t of x plus c sub 2 t of y. Now, formally, this is what it means for a transformation, a multivariable function to be a linear transformation. And this property here is known as linearity. It's known as linearity because what it means is that the transformation of any linear combination of two vectors or more is the same thing as a linear combination of the transformations of the original two vectors. And so this type of restriction on this multivariable function lets us talk about a lot of really nifty properties. Namely, since we know that any vector, say we're dealing in two dimensions, any vector in R2 can be written as a linear combination of our standard basis vectors. So in other words, say that the vector x, which has components, say, x1, x2, and that's going to be in R2, that means that x can be written as some constant times I hat plus some other constant times j hat. And so what this means now is that if we know what the linear transformation does to the two standard basis vectors, then we know what it does to any other vector in space, right? So let's say, for example, that the transformation, let's say that the linear transformation, we input I hat, we input, and I'll write it as 1, 0. Say that gives us 1, 3. And let's say the transformation, on j hat, 0, 1, gives us 2, 4. So what this means geometrically is that we apply our multivariable function, this linear transformation, and what it does is, so originally, here we have 2D space. This is originally where I hat is. And then after the linear transformation, I hat gets moved up to 1, 2, 3, up to here. This is the new I hat after the linear transformation. And then likewise with j hat, we're at 0, 1. We go to 2, 4. So 2, 4, like that. So this is what happens to these vectors after this linear transformation is applied. And now we know that, let's pick any old vector here for x. Let's say x is equal to the vector 2, 5. I'm just pulling that out of thin air, really. Then the transformation on the vector 2, 5, right? What is that going to be? It's really, if you think about it, it's the transformation of 2 times the vector 1, 0 plus 5 times the vector 0, 1, which is, by this property of linearity, which is so important, 2 times the transformation on 1, 0 plus 5 times the transformation on 0, 1, which we know what that is. That's 2 times transformation on 1, 0 is 1, 3, plus 5 times the transformation on 0, 1, which is 2, 4. And that's going to be the vector 2 plus 10, or 12, and 6 plus 20, or 26. And so now we can see that if we know what happens for all of the basis vectors in our space, we know what happens for any vector in our space. And I just picked that as an example here. So now, if we know what the linear transformation does to our two basis vectors, then that's essentially all we need to know about the linear transformation. And anything else further, we can deduce from the two, what happens to the two basis vectors. So what we're going to do is we're going to compactly write this linear transformation in terms of what we call a matrix. And what that matrix is going to represent is its columns are going to be the images of the standard basis vectors. So what I mean by images of the standard basis vectors is that that's where they land on after the transformation is applied. And this is really very important to remember here, which is why I wrote it down. This is essentially how we define the matrix to be geometrically. So we are going to amalgamate this information here into one matrix, and its columns are going to represent the images of the standard basis vectors. So its columns are going to be 1, 3, that's where I hat lands, 2, 4, that's where j hat lands. And so you see now that this matrix here actually represents something. It represents where I hat and j hat land after this linear transformation is applied to those basis vectors. So it's just a compact way of writing a linear transformation. Now, there are all sorts of things that you could talk about that make this make even more sense with other things that you may have seen. For example, with determinants, because with determinants, the determinant essentially measures how much the area has changed from the original. So originally, I hat and j hat span a 1 by 1 unit square with an area of 1. Now I hat and j hat span something really funky. Kind of like if I'm imagining like duplicating this red vector over here and then duplicating this black vector over here. They're going to intersect. It's going to be kind of a yucky shape, something like that. And so the determinant then of this matrix represents the area of this right here, what the images of the standard basis vectors now span. And this again makes sense as why we can only compute determinants of square, in other words, matrices that have the same number of rows and columns. We can only compute determinants of square matrices because, well, if we computed determinants of non-square matrices, the number of dimensions of our space wouldn't be constant. Now, it's totally okay for a matrix to represent a linear transformation between dimensions. The number of dimensions doesn't have to be constant. You know, for example, let's say I have the matrix 2, 1, 0, 3, -1, 0. What this matrix does, it's not square, right? It's got more columns than it does rows, but it represents a transformation from R3 to R2. In other words, 3D to 2D. And how do I know that? Well, because there are 3 columns here, that means that there were originally 3 standard basis vectors, which means we were in R3. And then where do those 3 standard basis vectors get taken to? They get taken to 2D, right? So I hat lands on this 2D vector 2, 1. J hat lands on this 2D vector 0, 3. And K hat lands on this 2D vector -1, 0. So in general, non-square matrices represent linear transformations between dimensions. Now, one last thing I would like to mention in this video is the idea of matrix addition and scalar matrix multiplication. So this is usually seen as a pretty natural definition, just because it just kind of seems like something that would make sense. But I want to kind of develop this definition a little bit more rigorously. So if we want to start out with, because we can define whatever we want with this new matrix stuff, but we want to define something that actually means something to us. So matrix addition, we want it to be so that, in other words, if I do a transformation T plus a transformation S on a vector X, I want it to be that if I were to apply the matrix A plus the matrix B on the vector X, I would get the same thing. Because a matrix is just representative of a linear transformation. So something that you would have to talk about first then is matrix vector multiplication, because right, we have A times vector X plus B times the vector X. So let's take a little detour there first. If we've got matrix vector multiplication, so I'll kind of write like a detour. If we've got matrix vector multiplication, we want the transformation on the vector X to be the same thing as if I were to just apply the matrix A on the vector X. So the matrix vector product, which is A times the vector X, is the result of applying the linear transformation on the vector X, which is corresponding to applying the matrix A on X. So what we're going to do then is let's consider what that matrix A might look like. I will write it like A. It's going to have, let's think of its columns for now. It's going to have a vector A1, A2, AN. And now I didn't write down all of the components of all of the vectors in the matrix, but I just kind of wrote it shorthand with these little dashes right here. And then the vector X, well, it's just going to have components, right, X1 up to Xn. And so this condition right here means that using the property of linearity, right, if it's a linear transformation, then that means X sub 1 times T of, and what I'm going to do is, since I'm dealing in n dimensions right here, I'm going to notate these standard basis vectors like this. E sub 1 with an arrow above it. In other words, that's like the first, quote, the first standard basis vector, plus X sub 2, T of E sub 2, and these are all standard basis vectors, plus ... plus X sub n, T of e sub n. And that's going to still be equal to a times the vector x. And so if I define, say I define t of e sub I, it gets taken to some other vector, a sub I. Then what this means is that x sub 1 times a sub 1 plus x sub 2 times a sub 2 plus dot 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 plus x sub n times a sub n is equal to a times the vector x. And this is what we're going to use as our definition for matrix vector multiplication, because it stems right from this original condition, which was a natural condition to impose. So if you look at this, right, what does this look like? It looks like a linear combination of the vector a, a1 through an. And so we can think of the matrix vector product, a times the vector x, as a linear combination of the columns of the matrix A, and where the components of the vector x are used as the coefficients of that linear combination. Now, if we're to write out this, if we're to write out like all of the components of all of these n vectors, right, we would get something like a sub 1, 1, a sub 2, 1, dot, 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 a sub n1, a sub 2, 1, a sub 2, 2, a sub 2, 2, 2, a sub n2, dot, 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 a sub n1, a sub n2, dot, 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 a sub nn, and then that is going to be multiplied by x sub 1, x sub 2, dot, 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 x sub n. Now, using our original interpretation right here, this is going to be a linear combination of the columns of A where the components of x are used as coefficients. So that would be x sub 1 times the vector a sub 1, 1, a sub 2, 1, a sub n1 plus x sub 2 times the vector a sub 2, 1, a sub 2, 2, a sub n2 plus dot 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 plus x sub n times a sub n1, a sub n2, dot dot dot, a sub nn. And now, if we are to think about this in terms of the rows of the matrix instead of the columns, right? So if we were to think about this of grouping it this way instead, then let's look at like just this first row right here when we actually do all this multiplication. We get x sub 1, a sub 1, 1 plus x sub 2, a sub 2, 1 plus dot 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 plus x sub n, a sub n1, which, if you think about it, this looks like a dot product, right? It's the dot product between the row vector, the first row vector, and the vector x. So if I consider the matrix instead as A being equal to, I'll use capital letters for the rows instead. So a sub 1, a sub 2, a sub, and it doesn't have to, the number of rows doesn't have to equal the number of columns, so I'll say a sub m. So it goes on like that. Then this is the dot product between a sub 1 and the vector x. And so an alternate interpretation is that, sure, a sub x, or I'm sorry, a times the vector x, matrix vector multiplication, if we look at the columns, a sub 1, I'll just do dot dot dot, a sub n times x sub 1, x sub n, then sure, this, you can think of this as a linear combination of the column vectors Or you can think of matrix vector multiplication. If we look at the rows, the row vectors, a sub 1 up to a sub m, multiplied by the vector x, as a bunch of dot products, where each of the rows are given by the dot products of the corresponding row vector of the original matrix. So a sub 1 dot vector x dot 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 a sub m dot vector x. So to solidify this as a concrete example here, let's say we wish to do the matrix vector product, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, times the vector 1, 2, 3. So the first way we can think about this is as a linear combination of the column vectors. So 1 times the vector 1, 4, 7, plus 2 times the vector 2, 5, 8, plus 3 times the vector 3, 6, 9, and sum that up, and we'd get 16, 26, 43. Or we can think of it as a bunch of dot products with the corresponding row vectors. So we can think of this also as, and this is going to get big, so we can think of this as 1, 2, 3, dot 1, 2, 3, 4, 5, 6, dot 1, 2, 3, 7, 8, 9, dot 1, 2, 3. And this is our new matrix. And you can see that you're also going to get here 16, 26, 43. So while at first, this might be computationally easier, this shows more conceptually what's going on in matrix vector multiplication. So, but either one works. But it's important to realize that they conceptually are talking about very different things. Now, finally, if we get to matrix addition and scalar matrix multiplication, we want, again, going back up here, we wanted the transformation on the vector to be the same as doing the transformation on the vector, and that transformation is the sum of the two matrices. So that it would be the condition for, I'll write it down here too. We want transformation on the vector x to be the same as what we would do to the vector x by the linear transformations represented by the matrices A and B. And for scalar matrix multiplication, we'd want, if I were to do some scalar times the transformation on x, I'd want that to be some scalar times the matrix on the vector x. And so if we consider, like, say the jth column, if we're looking at this here first, matrix addition, if we're to consider the jth column of A plus B, well, what is that? It's A plus B times the jth standard basis vector, which should be equal to the transformation t plus s on that same basis vector, which, since it's a linear transformation, it's the same thing as t of e sub j plus s of e sub j, which is going to be equal to, by our definition, a of e sub j plus b of e sub j. which is just the jth column of A plus the jth column of B. And so to get to how you actually multiply or how you actually add matrices, just add up the corresponding columns, right? You know, if I had 1, 2, 3, 4 plus 5, plus 5, 6, 7, 8, I would just get 1 plus 5 or 6, 2 plus 6 or 8, 3 plus 7 or 10, and 4 plus 8 or 12. But realize that this isn't just like convenient. It naturally comes from imposing the linearity condition, right? That a matrix is a linear transformation. And the argument for matrix, scalar matrix multiplication is almost exactly the same. I will leave that as an exercise to the interested viewer. And so I believe with that,